Next, we're going to talk about covalent bonds. Covalent bonds are very different. A covalent bond forms, excuse me, when atoms share two or more valence electrons. So with an ionic bond, we were actually transferring one electron from one atom to another. But with a covalent bond, we're going to share electrons. So here in this picture, we see an atom of oxygen, and it has 6 electrons in its valence shell. So it's not happy, it's not stable, right? It wants 8 electrons in its valence shell. And then same thing for this oxygen over here. It has 6 electrons in its valence shell. It's not happy, it's not stable. But what if those two oxygens came together and shared some electrons? If we count now, there is 1, 2, 3, 4, 5, 6, 7, 8 electrons in the valence of this oxygen. And let's count for this one too. 1, 2, 3, 4, 5, 6, 7, 8, right? So both of these oxygens now have 8 electrons in their valence shell, and they're both stable. And indeed, this is what oxygen gas looks like in an atomic model. There are different types of covalent bonds. We can talk about types of covalent bonds based on the number of shared electrons. So there are single covalent bonds, double covalent bonds, and triple covalent bonds. Each share a different number of electrons, 2, 4, and 6 respectively. We can also talk about types of covalent bonds based on how evenly the electrons are shared, and those are called polar and nonpolar bonds. So first we're going to talk about covalent bonds based on the number of shared electrons. In a single covalent bond, each atom is contributing an electron to the bond, so there are 2 electrons that are shared. With a double covalent bond, each atom is donating 2 electrons to the bond, so there are 4 altogether, so 4 electrons are shared in a double covalent bond. And then in a triple covalent bond, 6 electrons are shared. The strength of the covalent bond depends upon how many electrons are shared. So the triple covalent bond is the strongest, followed next by double and then single. And almost all covalent bonds are stronger than ionic bonds. All right, in this picture here, we see 5 atomic models, 1 of carbon and 4 for hydrogen. And no one here is happy. No one here is stable. Hydrogen does not have full valence shells. Carbon doesn't have a full valence shell. But what if we did this? Now, if you count, carbon will have 8 electrons in its valence shell. And each hydrogen has 2 electrons in its first shell, which is its valence shell. Don't forget that first shell is full with 2. So the valence shell is full on all these hydrogens too. These are examples of single covalent bonds. So we see 4 single covalent bonds in this picture. Here we see 2 hydrogens and an oxygen. No one's happy. No one has a full valence shell. Oxygen only has 6 electrons in its valence. What if we did this? Right? If you count, now oxygen has 8 electrons in its valence shell, and each hydrogen has 2 electrons in its valence shell, and everybody has a full valence and everybody's happy. This, of course, is water. So that was that previous example in water. Let me go back to that. These are also single covalent bonds. We see 2 single covalent bonds. Let's take a look at a double covalent bond, though. So I showed you this picture earlier. This is oxygen gas, and you can see here we have 4 electrons being shared between the 2 oxygens. The 2 blue electrons were donated by this oxygen, and the 2 orangish electrons were donated by this oxygen. Right? Both of the oxygens have 8 electrons now in their valence shell. Right? They're sharing these 4 electrons. That's a double covalent bond. Here we see an example with a double covalent bond and 4 single covalent bonds. Right? So here we see a double covalent bond between the 2 carbons. Right? We're sharing 4 electrons. That's a double covalent bond. Here we're sharing 2 electrons. This is a single covalent bond. Right? Another single covalent bond, another single covalent bond, and another single covalent bond. And last is the triple covalent bond. Right? This is nitrogen gas. So most of what's in the air that you're breathing right now is actually this stuff here, nitrogen gas. It's two nitrogens held together via a triple covalent bond. It's one of the strongest bonds on this planet. There are very few organisms that can actually break this bond. We can't at all. The nitrogen gas comes into our body and does nothing, and it comes right back out. But notice that we are sharing 6 electrons here. And also notice that both the nitrogens have 8 electrons in their valence shells, so they are stable. I want to talk a little bit about the different ways that we can talk about molecules. What we've been looking at so far are things called atomic models or Bohr models, where we're looking at like a pictorial representation of the atom or molecule. So we're looking at a picture with little electrons on it that is showing us a lot of information about the bonds and the electrons. Right? That's the atomic model or the Bohr model. Another way we can talk about these molecules, though, is using something called a structural formula. A structural formula will tell you what atoms are present. So the N stands for nitrogen, so we can see that there's 2 nitrogens. And the structural formula also gives us some information, sometimes at least, about the bonding between the atoms. So these 3 lines that we see here between the 2 ends, this is the symbol for a triple covalent bond. This here, N sub 2, this is also nitrogen gas. All of these are nitrogen gases. It's just different ways to talk about it, to write about it. The N sub 2 tells us that there are 2 nitrogens. This is the molecular formula. It tells you the number of atoms in the molecule, but it doesn't give you any outright information about the structure. Like, we don't know what kind of bond is present there. A chemist can look at that and tell you that it's a triple covalent bond, but we're not chemists. We don't know what kind of bond's there. Just looking at that N sub 2, we don't know that there's electrons being shared or what. So it doesn't give us as much information, but it does tell us the number of atoms in the molecule. And you'll be encountering all these different representations. Let's take a look at another example. These are 3 different ways to represent water. Up top here, this is the atomic model or Bohr model. Here is the structural formula for water. The single line between the H and the O represents a single covalent bond. And then, of course, you're likely very familiar with the molecular formula for water, H sub 2O. And now another example with oxygen gas. Here's the atomic model or the Bohr model. Right? Here's the structural formula for oxygen gas. The 2 lines here between the 2 oxygens tell us that this is a double covalent bond between 2 oxygens. And there are different ways we can write the molecular formula. We can do the O sub 2 or 2 O's together. More often than that, it's the O sub 2. Okay, so now that we know about the single, double, and triple covalent bonds, we can talk about classifying covalent bonds according to whether or not the electrons are being shared evenly. So here we're going to come across 2 categories, polar and nonpolar covalent bonds. But before we even talk about this, we need to understand a concept called electronegativity. So electronegativity is an atom's affinity for what? What does it sound like? Right? I mean, it looks like a big scary word, right? But you hear the word electron and you hear the word negativity. Of course, electrons are negative. So really, electronegativity is an atom's affinity for electrons. How well does the atom attract electrons? The word affinity means to love or to attract, kind of thing. So what do you think is in an atom that attracts electrons? Remember, electrons have negative charge. So what is in an atom that could possibly attract something that's negative? Right? If you thought protons, you're right. But there are other things besides protons that contribute to electronegativity. We're not going to get into that. If you want to learn about that, you'll have to take a chemistry course. Electronegativity is a standard unchanging property for each element. So every single element has its own standard electronegativity that doesn't change. Nitrogen's electronegativity is 3.04, oxygen is 3.44, hydrogen is 2.20, carbon's 2.55. This is a periodic table of the elements, and instead of giving you the atomic number or atomic mass, it's giving you the electronegativity for each particular atom. The darker the color, the higher the electronegativity, right? So you come over here, you can see oxygen and nitrogen are pretty dark. They have very high electronegativities. All right, what I'd like you to do right now is to consider these 2 different scenarios. Let's say we have 2 atoms with the same or similar electronegativities, and they're forming a covalent bond. So let's say we have two carbons that have come together, right? Carbon has an electronegativity of 2.55. The other carbon also has an electronegativity of 2.55. So what that means is that they both can pull on electrons the same, right? Think of this as like a tug-of-war match where the two opponents are exactly the same. They both have the exact strength to pull on the rope. Scenario number 2, we have two atoms with different electronegativities forming a covalent bond. Right? You have a nitrogen that has an electronegativity of 3.44, and that's bound to hydrogen that has an electronegativity of 2.20. In this tug-of-war match, there is clearly someone here that's stronger. And remember, what we're tugging on are the electrons. So what I'm asking you is, in which scenario will the shared electrons in the covalent bond, in which scenario will these shared electrons not be shared equally, and why? Right? So in the first scenario, you have two of the exact same atoms pulling on the electrons. Likely no one's going to pull on the electrons more than the other, right? The electrons that they're supposed to share will be shared equally. But when we have nitrogen and hydrogen trying to share electrons, clearly someone is going to pull stronger on those electrons. If the shared electrons from a covalent bond are not shared equally, then one of the atoms gets custody of the electrons more than the other atom. So if you were thinking that nitrogen is going to have those electrons more often than hydrogen, then you're correct. So in that scenario, what type of charge is going to start to develop around that nitrogen, right? If nitrogen is pulling the electrons toward itself more often and the electrons have a negative charge, what kind of charge will develop around nitrogen? If you said negative, you're correct. Though the nitrogen does not end up with a full negative charge, it does end up with a partial negative charge. Next question is, what type of charge will start to develop around the atom that does not get the electrons much? Remember, they have to share these electrons, right? So the other guy, the wimpy person in this tug-of-war match, gets the electrons sometimes, just not very much, right? So if they're not getting the electrons, they're missing that negative charge, and they're likely going to start to develop a partial positive charge. These are not full charges, these are partial charges. So let's take a look at this in a more pictorial format. Up top we see carbon and hydrogen sharing a pair of electrons, and then below we see oxygen and hydrogen sharing a pair of electrons. Carbon and hydrogen have very similar electronegativities, so that's the equal tug-of-war. So they both get the electrons the same amount of time. It's like 50-50 custody. Now down at the bottom with oxygen and hydrogen, oxygen is way more electronegative than hydrogen, meaning oxygen is really good at hogging those electrons. I don't let my little video stop. Let me start it up again. Whoops. There we go. So if you notice the electrons in the oxygen-hydrogen bond, those electrons spend a lot more time with oxygen than hydrogen. The electrons have a negative charge, so we start to develop a partial negative charge over on the oxygen and a partial positive charge over on the hydrogen. The reason why these aren't full charges is because the electrons don't move permanently. Right? Sorry, my electron's not moving. I don't know why, but pretend they're still moving. These are partial charges, not full charges, because the electrons don't move permanently from one atom to the other. All right, so with the upper scenario here, the carbon-hydrogen, that's a nonpolar covalent bond. With nonpolar covalent bonds, there's equal sharing of electrons. And this occurs when the covalently bound atoms have the same or similar electronegativities. It results in an overall equal charge distribution all around. You don't develop partial positive and partial negative charges. So some examples of this is when you have two atoms that are the same forming a covalent bond, like two carbons or two oxygens or two nitrogens. Those will always be nonpolar covalent bonds. Carbon-hydrogen bonds are nonpolar too. Carbon does have a slightly higher electronegativity than hydrogen, but not that much higher. So it's really negligible, so they both kind of share the electrons equally. Molecules that have lots of these nonpolar covalent bonds are said to be nonpolar molecules. The other type of covalent bond then is called a polar covalent bond. The Earth is polar, batteries are polar, these bonds are polar. The Earth is said to be polar because it does have a positive pole and a negative pole. Batteries are polar because they have a positive side and a negative side. A polar covalent bond has a partial positive side and a partial negative side. And in a polar covalent bond, this is caused by the electrons not being shared equally. Right? There's an unequal charge distribution. We call that polarity. And this happens when the covalently bound atoms have very different electronegativities. If you're a numbers person in this class, we're mostly concerned with differences in electronegativities of about 1 or more. And there's only 2 examples that you need to know. It's the oxygen-hydrogen bond and the nitrogen-hydrogen bond. Both of those are polar covalent bonds. Oxygen has a much higher electronegativity than hydrogen, so if the two come together in a polar covalent bond, oxygen is going to hog the electrons. Same thing is true for nitrogen. If nitrogen forms a polar bond, or excuse me, if nitrogen forms a covalent bond with hydrogen, then that's a polar bond because the nitrogen is much more electronegative than the hydrogen and it hogs the electrons. Molecules that have a large number of polar covalent bonds are called polar molecules. So this is an example of water, and water is a polar molecule. The blue arrows in this picture are pointing to the single covalent bonds that we find between hydrogen and oxygen in water. And this is an oxygen-hydrogen bond here, and that's one of the ones I said to look out for polarity. So these electrons that are shared aren't shared equally. They spend most of their time with oxygen. Same thing here. These electrons are not shared equally. They spend most of their time with oxygen. So the oxygen develops a partial negative charge, and the hydrogens develop partial positive charge. I have that little battery over there to remind you that batteries are polar, and this molecule is polar too, right? We're partially positive on this side and partially negative on this side. This symbol, by the way, is the Greek lowercase delta, and it means partial in science. So polar molecules, these are molecules with lots of these polar covalent bonds. These polar molecules have partial electrical charges. One area of the molecule is usually partially negative. I shouldn't say usually, it is. That's going to be oxygen or nitrogen. And the other part of the molecule is going to be partially positive, and that's hydrogen. The reason being, don't forget, hydrogen has a low electronegativity as compared to oxygen and nitrogen. So let's see if you can ID some of the polar and nonpolar covalent bonds here. We don't know what a lot of this stuff is on the screen yet, that's okay. You might recognize this down here. This is that oxygen gas I showed you. But you already know about structural formulas. So you know that the single lines mean a single covalent bond and the double lines mean a double covalent bond. So let's see if you can ID some of the polar and nonpolar bonds here. How about this one right here between a nitrogen and a hydrogen? If you guessed polar, you're correct, right? Nitrogen hydrogen bonds and oxygen hydrogen bonds are the only ones that you really need to worry about in this class as being polar. So carbon hydrogen. What do you think about this one? Is it polar or nonpolar? If you said nonpolar, you're right. Carbon and hydrogen have very similar electronegativities, and they'll share the electrons, so there won't be any partial charges that develop there. Between this oxygen and this hydrogen, there is an assumed single covalent bond, okay? And it's an oxygen-hydrogen bond, so red flag should go up. This is one of our polar covalent bonds. But here, carbon-carbon. If we have two atoms that are the same and they're forming a covalent bond, that's always going to be nonpolar. How about that carbon-carbon bond? Still nonpolar. How about that carbon-carbon bond? Still nonpolar. How about this bond? It's a double covalent bond. Is that polar or nonpolar? Well, we have two of the same atoms forming a bond, and that's the important thing. It's going to be nonpolar. Both of the oxygens have equal electronegativities, and they both pull the same on those electrons. Oxygen-hydrogen here, that's polar. Carbon-hydrogen, nonpolar. So review for covalent bonds. A covalent bond forms when atoms share electrons to achieve octet. The electrons are shared in pairs, right? 2 for single, 4 for double, 2 for single, 4 for double, 6 for triple. Sometimes electrons are not shared equally. If they're not shared equally, that creates polar covalent bonds, which creates partial charges. If the electrons in the covalent bond are shared equally, it's a nonpolar covalent bond.